Good afternoon, everybody. Welcome to those of you here in Strasbourg, and also to those of you who may be watching out on the internet, on the web stream. My name is Chris Welch. I'm ISU's Master of Space Studies Program Director. It's my very distinct pleasure to welcome you today to the culmination of 6 months of extreme effort by our MSS16 class. In the true tradition of ISU, they have executed two international, intercultural and interdisciplinary projects. There have been many late nights, there have been many weekends, there has been much blood, sweat and tears, and today you will see the results of that. We have two team projects. The first one will start in a couple of minutes. Then they will present for an hour. There will be half an hour of Q&A with members of the ISU faculty who are here present in the room, and possibly some externally sent in questions. Then there will be a short break while the second team set up, and then we will continue with the second presentation. So without any further ado, I would like to hand over to the first team, Team Project SEDNA, who are looking at planetary protection for Icy Moons missions. Thank you.
Thank you very much, Professor Welch. Welcome, everybody. Thank you for coming. Welcome to the presentation of the final report by the SEDNA team. It is a great pleasure to be here today to present our work, which is the culmination of the team's efforts, study, and research over the last year. As originally TP astrobiology, and we were inspired by the search for life and this quote. Before continuing, on behalf of the team, I'd like to give thanks to the many people who helped us, who helped assist, guide, and advise us during the entire course of the project. We would like to thank our faculty interface, Professor Hill, our dedicated TA, Juan Gramajo, and of course, the entire faculty and staff, and our absolutely fantastic librarian, Muriel Reister. Furthermore, our thanks go to world astrobiology expert, Dr. Chris McKay of NASA Ames, KNX Ethics Advisor, Dr. Jacques Arnaud, and European Science Foundation Science Officer, Dr. Manuel Detzis, and many MSS alumni who assisted us over the last 6 months as well. Mr. James Bevington, Dallas Kazabowski, Melissa Guzman, Adriano Skolemis, Zoya Nu, Karishma Inamdar, and Christopher Kenny. It is with great pride as well that I can announce that our project has been sponsored by NASA, specifically by the Office of Planetary Protection in the Planetary Science Division at NASA headquarters, as well as by the Planetary Missions Program Office at the Marshall Space Flight Center. Okay. I'd like to introduce you to our team. So this was Team Astrobiology at the start, a team of 20 students with 13 specializations, speaking 15 languages, who came together to study astrobiology this year at ISU. In this presentation, we will present everything in the same order as we did in our final report. Shantini will begin by talking about cultural and ethical drivers, because as we know, all rationales for everything are cultural. And then we will discuss rationales for missions to icy moons and planetary protection in those missions. This will be followed by an introduction into the existing international policies and management structures for planetary protection. Martina will then give an overview of the science of icy moons and highlight the moons of particular interest to astrobiologists in the outer solar system. Immediately following this is a description of several planned missions to Jupiter, to Jupiter's moons, and conceptual missions to Enceladus. Each of the given missions is designed to search for life on these other worlds. So following this, John will come up and discuss a set of advanced concepts, and will give the audience a broader view of the missions and methods for searching for life in the icy moons. This will be followed by an introduction to our analysis of the NASA technology roadmap. So John will then present the first of our major proposals resulting from this project, which will be a prioritization of technology development in terms of its benefit to planetary protection in missions to icy moons, and indeed for all missions. The culmination of our presentation is a description of our final proposal, which will be given by Alexandra. We will propose the development of technologies for the development of an orbital platform called SEDNA to support planetary protection in these missions. So why did we choose planetary protection and icy moons? Well, our team started off studying astrobiology, which is the study of origin, evolution, and distribution of life in the universe. In recent years, the astrobiology community has become increasingly interested in icy moons of the outer solar system, such as Enceladus, Titan, and Ganymede. And so the topic of planetary protection in missions to these icy moons was deemed timely for our team. As you know, at the start of the year, our team was known as TP Astrobiology, but we changed our name to Team SEDNA during the course of the final report. SEDNA is the Inuit goddess of sea and marine animals, and so we decided this was a fitting name for our project due to its focus on missions to celestial bodies that oceans that may sustain life. So throughout the presentation, we will be presenting our interdisciplinary analysis of these topics. We will make conclusions and recommendations at the end of each section. In the end, these conclusions and recommendations lead to 2 proposals from our team to help address these recommendations. So the first proposal will be for modifications to the NASA technology roadmap, and the second proposal will be for our platform, the SEDNA platform, details of which I will leave to be presented later. I will now pass the floor to my colleague Shantini, an aeronautical engineer from India, who will begin by talking about the rationales for missions to icy moons and planetary protection. So everyone, please welcome Shantini.
So thank you, Stan. Today I'll be showing you the cultural drivers for planetary protection. Starting with the cultural drivers, the driving rationales for the search of life and planetary protection take inspiration from 2 science fiction themes, namely the protection of humanity from aliens, and the other is the protection of aliens from humanity. These science fiction themes are surprisingly universal and cross-cultural. The first theme, that is the protection of humanity from alien invasion, which has a long history in science fiction from 1897 publications of S.G. Wells' The War of Worlds. Alien invasion narratives can be found in most popular Hollywood blockbusters such as Independence Day, Simon Pegg's 2013 film The World's End. Many cross-cultural examples like the very popular Chinese trilogy The Three-Body Problem, and many examples of Japanese manga and anime, including the Macross series from the 1980s, spawned multiple sequels utilizing this theme. Next is the protection of aliens from humanity. Science fiction works long concerned with the protection of alien from humanity, as evidenced in Star Trek concept of Prime Directive and the Arthur C. Clarke concept of Star Child. These concepts have developed from moral and ethical issues involving clashing cultures to more basic personal or biological imperative to protect life in any form that may or may not be intelligent, and finally to a concept of protecting an environment or ecosystem that may harbor life in many forms. An example of this is the Japanese anime classic Nausicaa of the Valley of Wind from Hayao Miyazaki, which tells the story of several human cultures fighting over whether to exploit, destroy, or live in peace with other life forms. Next, we will be seeing the rationales for planetary protection, which is classified into 3, namely the scientific rationale, social rationale, and ethical rationale. All these rationales have been historical drivers of planetary protection laws, international agreements, scientific assessments of threats and risks, management policies, and even technical procedures developed as a result of these policies. So, first, the scientific rationale. The scientific rationale is relatively straightforward, which states that any observation of phenomenon will have an effect on that phenomenon. The goal of discovering a new life requires a utilitarian approach. we must be sure that if we find any life form in a solar system, and it shouldn't be the life that we bought from there. Social rationale. The social rationale extends from the principle of protecting astronauts and humankind from the harm. This is embodied in the basic principles outlined by the NASA's Office of Planetary Protection as a part of planetary protection policy. It is necessary to predict and prevent, or at least limit, the biological contamination in the best way possible to reach a better understanding of both extraterrestrial environments and terrestrial microscopic life forms. Moving on to the ethical rationale. The ethical rationale stems from cultural views that humanity has too far over the Earth and maybe the universe. The main question is whether humanity has an obligation to protect celestial environments in their own sake, not for any human utility. There are few challenging ethical questions such as, is it ethical to contaminate another celestial body? How much do we need to know? What kind of putative life is important enough to require protection and what is not? 2. Non-living things deserve self-respect and conservative status. What is our responsibility to future generations? Concluding this section, there are strong cross-cultural concerns for alien invasion and therefore strong cross-cultural motivation to come to agreement on backward contamination. There are also cross-cultural concerns for the preservation of life and environment which tend to support forward contamination policies. And few recommendations are given to increase international support of planetary protection concerns for self-preservation against alien invasion could be used as a cross-cultural motivator. Outreach programs for planetary protection may reach broader audiences by aligning themselves with the launch of popular movies and novel franchises. Followed by this will be the planetary protection policies and management. Starting with COSPAR, the Committee on Space Research is an international scientific organization with a subcommittee that makes recommendations on planetary protection. There is no international treaty specifically endorsing COSPAR policies. Nonetheless, nations tend to follow COSPAR. This subcommittee has been historically dominated by Western agencies like NASA, ESA, and Canadian and Japan space agencies. The purpose of COSPAR includes hosting biennial academic conferences, publishing journals, hosting workshops for emerging space nations, creating and executing outreach plans, advising government and non-governmental organizations on research and space-related issues, setting guidelines and standards for space-related research. Here you can see the planetary protection policy process. The COSPAR policies are in flux and updated as new missions are proposed and new requirements arise. The policy development process for COSPAR involves continual solicitation of input from the scientific community, both from regular scan of peer-reviewed scientific literature and from time to time COSPAR-sponsored workshops on particular topics. As shown in the figure, you can see there's once a planetary policy has to be introduced, when a new phenomenon or a new mission arises, possible suggestions will be given by the scientific committee, and a panel meeting will be held. Panel recommendations will be voted by the Bureau and Council. Based upon that, a new policy will be created. Moving on to the COSPAR participation. This is a chart showing countries' participation in COSPAR planetary protection policies during the year 2002 to 2013. You can see, unfortunately, COSPAR planetary protection meetings are attended mainly by the Western countries, which is not a great example of international cooperation and agreement. In this chart, you can see North America and Europe plays a major role in all these years, participating in most of the meetings, whereas Russia stopped attending meetings since 2009, whereas other countries has less or zero contribution towards it. Moving on to NASA planetary protection structure and management. The role of Planetary Protection Officer is created and defined in the NASA Policy Directive NPD 8020.7G by authority of NASA Administrator. NASA Planetary Protection Officer reports to the Deputy Administrator for the Science Mission Directorate. The figure depicts the Planetary Protection Officer's role within the NASA Science Directorate organizational hierarchy. The PPO or the Planetary Protection Officer has direct oversight over robotic interplanetary missions that are usually driven by this directorate. However, the PPO has only indirect oversight over human missions and space technology developments. ESA, the European Space Agency, like NASA, has a dedicated PPO to oversee planetary protection measures. The ESA PPO works closely with their counterpart at NASA to maintain continuity among the planetary protection policies among cooperating space agencies. Currently, ESA PPO Gerhard Kühneck sits as the COSPAR chair, while the NASA PPO Casey Conley sits as the vice chair, along with Victoria Hepkin of Canadian Space Agency and Hajime Ano of Japan Aerospace Exploration Agency. Here you can see other nations in planetary protection: CNSA, or the China National Space Administration, and ISRO, Indian Space Research Organization. The existence of the planetary protection in both offices is not formally identified, but methods of contamination mitigation could still be implemented as a room procedure. The Roscosmos, Russian Federal Space Agency, does not have a dedicated office for planetary protection and had a little participation in COSPAR Planetary Protection panel meetings since 2002. This seems to be changing recently due to Roscosmos' partnership with ESA on ExoMars, which has resulted in several papers being published by Russian scientists to COSPAR meeting in recent years. Finally, concluding this topic, conclusion. Western nations and their space agencies, particularly North America, Europe and Japan, tend to participate more in COSPAR planetary protection panel meetings, and therefore they dominate in the policy generation process. International partnerships like ExoMars have been proven to bring more varied international participation to COSPAR planetary protection policy meetings and assemblies. The NASA Planetary Protection Office gives its science directorate may have limited influence in planning human missions and technology developments. Recommendations: all nations should be encouraged to participate in COSPAR planetary protection meetings and scientific research regardless of their mission profiles, since prevention of backward contamination is a universal concern. All nations with space programs should be encouraged to collaborate on interplanetary missions, as this will help to bring more players into planetary protection policy process. Thank you. Now I pass the floor to Martina.
Thank you, Shantini. So, in this part of the presentation, we will discuss the science of icy moons. In particular, we will answer to the interrogatives: what are the main features of icy moons, and why are we interested in icy moons? And we will also describe the main subjects of interest for future missions to icy moons. The icy moons orbit around large gaseous planetary bodies and lie beyond the ice line of the solar system, where gases typically condense. In particular, missions to Jupiter and Saturn systems have shown a significant potential of discovering life in the outer solar system and around their numerous satellites, thus garnering interest within the planetary science community. Saturn possesses a diverse array of moons, totaling 62, mainly discovered by Christian Huygens, Giovanni Domenico Cassini, and William Herschel. All these moons, Titan and Enceladus, have proven to be some of the most promising in the context of astrobiology. Jupiter has 67 known satellites in orbit. 4 of them, the so-called Galilean satellites, were first discovered by Galileo Galilei in 1610. These moons, Io, Europa, Ganymede, and Callisto, possess characteristics deemed important for further studies. Among them all, Ganymede and Europa are primarily candidates for astrobiology research, thus rivaling Saturn's moon, Titan, and Enceladus. Sorry. So, now I will describe some of the main features of these 4 moons I mentioned, starting with the largest moon in the solar system, Ganymede. Ganymede's composition is characterized by a metallic core, a rocky mantle, and an icy shell. It has an intact magnetic field, most likely originating from the metallic core, which could provide radiation shielding as well as generate energy able to produce hydrothermal vents on its subsurface ocean floor. It is thought to have plate tectonics, which is supported by the existence of darker, heavily crowded regions, contrasted by younger, lighter grooved regions named sulcus and comprising 60% of the moon's surface, and possibly created by the subsurface ocean. Its geological evolution is blunted by its gravitational interaction with planet Jupiter. Passing to the second of the Jovian moons, Europa, it has long been considered one of the most promising locations in the search of life in the solar system. It has a structure which is very similar to Ganymede, characterized therefore by a metallic core, a rocky mantle, and an icy shell. Talking about its dimension, it's slightly smaller than the Earth's moon. Its surface is icy and fractured, with a saltwater ocean underneath, which would be a prime environment for any developing life. Its existence was proven by Galileo mission, launched in 1989. It was found that Jupiter's magnetic field was altered around Europa, and thus indicated that electrically conductive fluid was flowing below the mantle. By combining this result with some features of Europa's magnetic field, the scientific community came to the conclusion that a massive saltwater ocean lies beneath Europa's surface. Europa is also tidally locked to Jupiter, therefore it reveals always the same face to it. Its surface is perturbated, cracked, and flexed by Jupiter, Ganymede, and Io's tidal forces. Plumes of water vapors have been observed and are ejected from the surface. They might be originating from the lines of Europa's surface and tied to the tidal effects of Jupiter, as they are observed to be active in the apogee of the orbit and inactive in the perigee. Extremely thin atmosphere have been observed on Europa, with a surface pressure of 100 billionth that of Earth's atmosphere. Now let's pass to the Saturnian system and let's see some of the main features of Titan. Titan is Saturn's largest moon and the second largest moon in the solar system. It has a volume which is similar to Mercury and is characterized by an extremely dense atmosphere of methane as well as extremely cold surface, as it received only 1% of the sunlight that Earth receives. Its surface is dominated by mountains and liquid methane lakes, with the largest being Kraken Mare. It also presents some deserts around the central equator and a subsurface ocean. The existence of rainy seasons has been proven, as well as the presence of active seasonal cycle. To conclude with the icy moon description, we got Enceladus, which is of great interest to astrobiologists today due to its unique characteristics. It has a liquid water ocean beneath the icy surface, whose existence was confirmed by Cassini mission, which showed that Enceladus had a wobble during its orbit around Saturn that could only exist if the surface ice was free-floating on a global ocean. It has an extremely cold surface temperature due to the high albedo, but strong tidal forces due to the resonance with Saturn's moon Dione heat the moon's core and consequently the subsurface ocean. Geologic and geothermal activity suggested by the presence of both young and highly cratered areas are thought to renew part of the surface. Another key characteristic of Enceladus are its plumes, erupting at high rate of speed and composed mainly by water vapor with smaller percentages of other components such as molecular nitrogen, methane, and carbon dioxide. By analyzing the main features of Jupiter and Saturn's moon, we can conclude that sampling from Enceladus geysers should be made the highest priority mission, as by ejecting organic compounds into space, these geysers simplify the acquisition of samples from the interior of Enceladus ocean. The second priority should be surface sampling and sample returns on Enceladus, due to the great chance of achieving important scientific results from direct surface contact and to the relatively small gravity well of this Saturn's moon. In this section of the presentation, we will explore the question, how do the major space agencies plan to study and gather scientific data from Jupiter icy moons? And we will do that by analyzing 2 missions to Jupiter and its icy moons. These missions, currently in developmental phases, are titled Jupiter Icy Moon Explorer, JUICE, and Europa Multiple Flyby Mission from ESA and NASA, respectively. The Planetary Protection protocol for both missions will be also presented. The JUICE mission consists of a planetary science orbiter and a launch vehicle for the deployment of the orbiter. After launching from an Ariane 5 rocket in 2022, the JUICE spacecraft will cruise for 7.6 years to Jupiter, with multiple gravitational assists from Earth and Venus. Following this cruise and insertion into Jupiter's orbit, JUICE will visit most of the bodies of the Jovian system, including Callisto, Europa, and Ganymede. At the end of the nominal mission, JUICE will be disposed of on Ganymede's surface in 2033. The scientific objectives of JUICE missions are aimed to answer the questions: what are the conditions for planet formation and the emergence of life, and how does the solar system work? To do so, Ganymede will be examined for a possible ocean, as well as its icy shell and its local environment, surface feature, and global composition of surface materials. In Europa, thermally active zones where liquid water may exist will be studied primarily. In addition, no water ice surface materials, atmospheric conditions, and its active process will be examined. Callisto's outer shell will be characterized, as well as the composition of its non-water ice material and past activity. Jovian atmosphere and magnetosphere will be examined with particular focus on the atmospheric dynamics and circulation, composition, structure, and clouds, and the magnetosphere 3 main regions. Moreover, the satellite and ring system of Jupiter will be studied by observing high-Earth volcanic activity and determining its surface composition, and by characterizing the ring of Jupiter and the small satellites found within the Jovian system. Now let's take a look at the second mission, Europa Multiple Flyby. Similar to JUICE, flyby consists of a spacecraft and a launch vehicle to send the orbiter to orbit around Jupiter. However, where JUICE will visit several of the icy moons, flyby will make 45 flybys of Europa only, thus maximizing data collection and transmission and mission duration. This mission will launch no earlier than November 2021 and spend 3 years in a direct unassisted cruise orbit to Jupiter. Flyby's repeated orbits are expected to last up to 3.5 years, during which it will image, characterize, and investigate Europa's icy surface and interior. The aim of the mission is to bring a better understanding of issues of habitability in the solar system by focusing on the research of the 3 ingredients for life, which according to NASA are water, chemistry, and energy. Water will be investigated through confirmation of an interior ocean and further study of Europa's ice shell, thus potentially learning more about the thermal processing properties of the shell, the exchange dynamics between the shell and the underlying ocean, and the tectonic layout of the Moon. By gathering data about the composition of materials found on Europa and studying the interaction of its organic and inorganic compounds, a better understanding of its chemistry will be brought. Linear features, chaotic terrain, impact features, and geological history will be analyzed in order to look for geological processes indispensable to provide energy for the genesis of a possible life. As both JUICE and Europa multiple flyby do not intend to come into contact with planetary bodies, they are considered Category 3 missions by COSPAR. Therefore, planetary protection is primarily concerned on contingency planning against failures that may cause an unexpected crash and planning for end of life. Bioburden reduction on the craft itself needs to be sufficient to bring the overall probability of contamination below 10 to -4. The chance of crashing during close passes to the targets are another main focus of planetary protection preventions. The key strategy for minimizing this probability will be to add as much precision testing and verification of the flight dynamics as possible. In light of the architectures of these two missions to Jovian system, we can therefore conclude that the planetary protection requirements for both JUICE and Europa flyby are relatively straightforward, focusing on the flight dynamics, probabilities of accidental impact, and the plan for end of life. The science value of these missions will not be as profound as a lander mission or a sample return mission, since direct contact is not part of the mission plan. Now let's take a look at some mission concepts to Enceladus. During Cassini mission, Enceladus has been identified as one of the most promising targets for extraterrestrial life detection. By using today's high mass resolution spectrometers and cutting-edge instrumentation, a unique opportunity to unveil the possibility of life evolving in the outer solar system arises. Two mission concepts have been proposed: Enceladus Life Finder, ELF, and Life Investigation for Enceladus, LIFE. ELF is a mission concept proposed by NASA and encompassed within the 2015 Discovery Program. It is a low-cost and highly effective mission concept. Its main focus is the characterization of Enceladus cryovolcanic activity and subsurface ocean. The mission objective of the ELF mission can be divided into three different categories: evolution, habitability, and life. The scientific objectives for each of these categories are respectively to study whether volatiles and organics coming from Enceladus have evolved over time due to its endogenic thermal activity, to characterize the internal ocean of Enceladus in order to ascertain its life-carrying capacity by measuring acidity, temperature, oxidation state, and available energy, to measure the plume composition with the aim of finding organic traces and biochemical signatures. So, three tests will be performed in order to achieve these scientific objectives. One will be a search for the clear patterns of amino acids. The other would be an analysis of the carbon number distribution within isoprenoids. And the last would be some measurements on the abundance of methane and carbon-hydrogen ratio. To guarantee a potential detection of life, these tests have been to be designed so that they are clearly differentiable, they look for properties inherent to life, and they are universal for water-based life. Talking about the other mission concept, life mission concept is based on the capabilities of Stardust mission and consists in a low-cost sample return mission. Its mission objectives are to capture, preserve, and return Enceladus plume samples, and to make complementary in situ measurements of Enceladus, the Saturnine ring, and Titan with high sensitivity and mass range instruments. The architecture of the mission is characterized by two main phases: an orbit around Saturn in order to achieve lower speeds for sampling, around 2 kilometers per second, and possibly make multiple flybys of Enceladus. A second phase will consist in sampling Enceladus plumes, the E-ring of Saturn, and Titan upper atmosphere. The total lifetime of the mission would be 13.5 years, and it will be launched on an Atlas IV rocket by 2019. Despite some similarities between the two mission concepts, by comparing them from the point of view of planetary protection, it emerges that they belong to different categories according to COSPAR criteria. In fact, when life envisages sample return, thus belonging to category 5, ELF is a simple flyby mission and therefore belongs to category 3. From what has been now discussed, we can therefore conclude that the ELF mission concept is technically simpler than the life mission. However, the ELF mission neither touches the surface of Enceladus nor returns a sample. Hence, it is limited forward and backward. Due to the fact the life mission concept envisages sample return, it consequently invokes the strictest possible planetary protection controls, which result in a considerable increase of the costs of the mission. Higher costs and mass are also a consequence of a need of controlled re-entry and landing systems required if we want to carry larger samples. In light of these conclusions, we recommend cooperation between agencies, as it will allow planetary protection cost sharing. Finally, yet importantly, as large samples are preferable for scientific studies, we believe that an Earth orbiting platform would be a good alternative for returning samples to Earth, as we will see more in detail soon in this presentation. Now, I have the pleasure to pass the microphone to my colleague Jonathan Stimmer.
Hello, everyone. So we just heard about some mission concepts, and here are some more. Okay, so first we'll talk about one to the Saturn's moon Titan. So it would consist, of course, of an orbiter, and it would then have a balloon which would go down to the surface and actually land a craft that would land on the Ladea Mare by 2030. And it has the potential, actually, of being the first craft to land on another liquid body in the solar system, outside of Earth, of course. Another mission concept would be the Enceladus Explorer, which is a project under development by German Aerospace Center, DLR. It has the capability to deploy a lander, the ISMO probe, as well as the ISMO will drill down to about 100 meters to breach the walls of an aqueous fracture, where it's believed that valuable samples can be found in the subglacial liquid flows. Issues such as energy source and instrumentation, of course, still remain. Another would be high-velocity impact missions, such as the ESA-CLEP, the Clipper Europa ESA Orbiter or Penetrator, and of course would be a mission to be a possible payload on the NASA flyby mission, formerly known as Clipper. It's designed to impact, then drill and melt the surface. The biggest concern, of course, is forward contamination of the surface. And of course, dry heat, chemical sterilization of impactor and instrumentation is recommended. Okay. And here it is up here. And then we have the next slide. Okay, so we also have submersible vehicles. There are two different kinds of submersible vehicles. One would be the AUVs, or the autonomous underwater vehicles, and the other would be ROVs, which are remotely operated vehicles. And of course, the Daedalus Century mission, as well as the Titan submersibles, would be two examples of such missions. And we'd really, again, be talking about the AUVs due to the, of course, distances involved of going across the solar system, things such as the time taken for communication, as well as the difficulty of communicating as it goes to deeper depths. We'd want some kind of autonomy. And of course, we have challenges with Europa missions, such as the penetrating the initial 20 to 30 kilometers of surface ice, and of course, again, the forward contamination question still remains. Okay, so from looking at these missions, we've drawn some conclusions. The first one being that orbiters, landers, drilling rigs, high-velocity impact missions, and submarines all require adherence to planetary protection guidelines due to their contact with environments that can harbor life. Planetary protection is difficult to fulfill for large landers, drilling rigs, impact missions, and in particular, submarines, because large-scale heating chambers and highly sterile assembly areas are needed. The mission concepts that are presented here can collect large samples, probe deeply into surface or subsurface regions, or explore oceans. All concepts provide more opportunity for analysis and hence are of interest to the scientific community. And from these conclusions, we've drawn some recommendations. The first one being focus should be made on missions that provide large sample analysis, such as drilling missions, or on missions that probe the surface or subsurface oceans, such as the high velocity impact and submarine concepts. Technology developments should be made to support the mission concepts and maintain sufficient levels of planetary protection. So I'll now be moving on to the technology roadmaps. Okay. And in 2015, NASA issued an updated technology roadmap for interplanetary exploration, assessing the impact of different technology on planetary protection. There we go. Okay. So for the NASA budget strategy for tech development, there's a relationship between NASA Tech Roadmap and NASA Strategic Space Technology Investment. Planet and Tech Board databases have as follows. The technology roadmaps guide the development of space technologies. The investment decisions for the technologies in the roadmap are specified in the Strategic Technology Investment Plan. And NASA's technology investments entered into TechPort, an online database and decision tool, and it's for tracking and analysis. Okay. So when looking at the technology roadmaps, we used a four-point approach in our methodology. The first one being, of course, the identification of the timeline, planning for upcoming mission programs, including, of course, Discovery and New Frontiers. The second point being identification of technologies. And this was already identified by NASA as important for the upcoming Discovery and New Frontier missions. So for number 3, we evaluated the technologies based on their relevance to architectures discussed as ELF, Life, Submersible, and Drill missions. And then finally, we assigned a scoring to each technology. So it was from a -5 to a +5, and this was based on the impact on planetary protection for these missions. Score of high compatibility with planetary protection, and a -5 would require demanding requirements for planetary protection. Okay, and so here's an example of the tech roadmaps. We took a few different areas. The first one we're going to start off with is the NASA Technology Area 3, Space Energy Storage. But before I go into this, I just kind of want to explain what this chart means. So the numbers on the left here, those correspond to tech in the NASA roadmap, and each one of these numbers has been assigned an actual technology, some of which I'll be listing in shortly. And the color bands show transition from actual So the number of color bands that we need to traverse in the time frame available shows the difficulty of the development endeavor. So the more color bands, the more difficult it is. And so the milestone bands, which we can see here, here, and here, are the launch dates of certain missions in budget, such as the New Frontiers or Discovery missions. So for the NASA Technology Area 3, or TA3, it's a grouping of space power and energy storage technologies under development for various space missions. In this section, we have selected these following technologies: solar cell improvement, radiation shielding, ion propulsion, and RTGs, and higher power electronics. So as far as the scoring we gave it, power generation technologies involving radiation can cause harm to any life encountered. Radiation tolerant technology can reduce risk of forward contamination and malfunction during flight. Okay. So moving on to Technology Area 8, it's Science Instruments. So for Technology number 8, these are also a bunch of under development for various space missions, and undeniably, of course, the most important aspect of astrobiology missions to the icy moons is the science undertaken on the environment once there. And as far as the planetary protection scoring that we gave it, remote sensing technology is usually best for planetary protection, as you're not making direct contact with samples and therefore reducing contamination risk. And so they therefore score high. Direct, also known as wet sample collection, usually is higher risk for planetary protection, and thus expensive sterilization is required. Okay, moving on to NASA TA9, we have entry, descent, and landing systems. So NASA technology in this section, we selected technologies that aid thermal protection on entry, as well as systems that improve reliability and accuracy of descent and landing, and of course primary sensors and autonomous landing systems. And as far as the planetary protection scoring we gave it, entry, descent, and precision landing techniques usually score high, as the nature of the technology is to prevent malfunction that could cause damage to the exploring craft, and therefore by reducing this risk, we also reduce the risk of forward contamination. Okay. Now moving on to tech area 14, thermal management systems. So this is a grouping of technologies under development as well, and the proper management, of course, of thermal control both before and after launch can reduce risk of failure and thus contamination. And as far as its planetary protection scoring, for thermal management, we, of course, developing better cooling technologies may offset damage from RTGs and reduce the grade of equipment, and so we gave these technologies relatively positive scores. Okay. All right, and then we have NASA Tech Area 7, Human Exploration Destination Systems. So this is actually where we kind of found a gap in regards to sample return and planetary protection. The risk of backwards contamination from outer space is great on any sample return mission. So we have explored this gap and may be able to address it by exploring TA7, human exploration technology, such as an orbiting platform. So, and as far as course of scoring goes, in orbit handling of samples, it's crucial, as this could prevent backwards contamination and re-entry, on an arrival on the Earth's surface. So milestones for this one shows the expected start date for the SEDNA mission, which we'll be talking a bit about later. Okay, so some conclusions. Power generation technology involving radiation can cause harm to any life encountered. So radiation tolerant technology can reduce risk of forward contamination and malfunction during flight. Remote sensing technology is usually best for planetary protection and scores high. Direct wet sample collection usually is higher risk for planetary protection, and so expensive sterilization is required. Entry, descent, and precision landing techniques usually score high, as the nature of the technology is to prevent malfunction that causes damage to the exploring craft, and therefore reducing risk of forward contamination. For thermal management, developing a better cooling technology may offset damage from RTGs and reduce the grade of equipment. And finally, in orbit, handling of samples is crucial, as this could prevent backwards contamination on re-entry or arrival on Earth's surface. And then finally, we have some recommendations, the first of which is we recommend that NASA prioritize budget allocation for technology development on the basis of planetary protection benefit, which we've presented here. We recommend that other space agencies also develop technology roadmaps with a scoring indicating the planetary protection benefit for use in setting budget allocation for tech development. And then finally, we recommend that the space community study in greater detail the possibility of combining technologies from robotic mission infrastructure as well as human near-Earth capability to create more robust sample return mission architectures. As a step in this direction, we will propose the SEDNA platform. And now I'd like to pass the floor to Alexandra. Thank you.
Good afternoon, everyone. Welcome. As John just said, I will give you a brief summary of what we've already heard from my colleagues, and then I will bridge into our main proposal, the SEDNA platform. So, first of all, Shantini took us through the drivers of planetary protection. Not only is there the age-old question of whether we're alone in the universe, she also discussed how backward contamination in regards to invasion of Earth by other species and forward contamination in regards to the potential of ruining other planets, environments, or potential life by infecting them with stuff that we bring with us, is cross-cultural concerns. Nonetheless, these cross-cultural concerns have not led to any international legal consensus yet, and we therefore encourage that there will be an improvement on this field in international cooperation. Further on, Shantini took us through the Planetary Protection and COSPAR regulations. She told us how the COSPAR is predominantly dominated by Western influence in regards to the North American and European countries. And nonetheless, it has been shown that international cooperations when it comes to planetary protection missions or astrobiology missions improves the COSPAR attendance of other countries. And therefore, we encourage further collaborations when it comes to astrobiology and planetary protection missions to enhance the development of a international cooperation on policy. Hereafter, Martina took us through the science of the icy moons. She told us how Enceladus is one of the favored candidates and that it actually provides free samples through the plumes of, from the geysers on the surface. She told us how these free samples are a very good opportunity for getting scientific information. However, surface or subsurface samples will provide much more scientific significance. And we therefore encourage that the first step is sampling from geysers, nonetheless moving on as quick as possible to subsurface or surface sampling from Enceladus. Hereafter, she took us to Jupiter and Jupiter's moons, and she described a couple of the planned missions that are under development at the moment, the Europa flyby and the JUICE missions, and how none of them actually plan for any contact with the icy moon environments and therefore provide less scientific significance and value than could be hoped for. At the moment, no planned missions actually provide any contact with icy moons, and we feel that that is a hole in the planning. So, both John and Martina took us through to elfin life missions and alternative mission concepts. It was described how if we go into the simplicity of a mission and thereby make it more feasible, we also at the same time have to go down on the value of the science that we get out of it. This has something to do with sample returns. They provide a much stricter planetary protection requirements that we need to follow, thereby increasing the cost and making the missions less feasible. Further on, ballistic re-entry, which is the way that it has been planned so far and been looked into, limits the sample size as the technology needed to do this will demand parachutes and heat shields, which is both increasing the technology and the cost of the missions. Concepts that provide contact with the moon will thus provide better opportunity for scientific significance. They will lead to a stricter adherence when it comes to the guidelines of planetary protection, and they will lead to funding and technical difficulties. So we encourage, based on these things, that as large sample as possible will be achieved when we go for samples on the icy moons, so as to get as much a high scientific value for money as possible. Also, we encourage that they're looked into alternatives of the re-entry instead of the ballistic method, as this will cause extra cost. And we definitely encourage agency cooperation so as the basal cost of planetary icy moon exploration can be shared between different states. Last but not least, we think that the technology development should support the missing concepts and the ones that are needed, so as to not develop anything further and thereby spending more money on things that are not necessary at the moment. That leads us to the technology roadmap that John took us through. where it once again was very clear that the more contact we demand of the mission, it gets a lower score because the complications increase thereby. This is seen in regard to remote instruments, where the score is high because we don't affect the environment as much. It's seen in the sample collection, and it's definitely seen with entry, descent, and landing system because they provide a better control and thereby decrease the risk of unintentional harm to the environment by, for instance, crashing into a lake where we thought that the risks of the chances of life would be the highest. Last but not least, in-orbit handling and processing of return samples will decrease the risk of backward contamination, as we would get an environment where we can further investigate the samples we bring back before we actually introduce them to our home planet. Therefore, we mean that certain technology development should be prioritized in order to better implement planetary protection in missions to icy moons. And this especially goes for the sample return missions. So, bridging into what is our center proposal, the SEDNA platform. The SEDNA platform would be a concept of a platform in LEO, the low Earth orbit, where it has been built around the conclusions and the proposals that are drawn throughout the whole report in our presentation here. It would be a crewed platform, and it would act as an intermediary point between the icy moon and the Earth, so kind of a bottleneck before we do more harm than is good. It will have the potential to both provide scientific experiments, so we can inspect what we're getting back, and at the same time, the opportunities of performing quarantine if we need this, both to samples and to the astronauts on board. The rationales for SEDNA have been discussed throughout this presentation, and the central ones are definitely that we decrease the risk of backwards contamination by introducing this bottleneck. It is that if we need to bring back the samples to Earth as the first way, this will mean that we're reaching a COSPAR Category 5, which introduces very strict requirements on our mission and pretty much makes it impossible for us to fulfill. International collaboration on planetary protection will also aid us in this way, because it will be possible for several agencies to work together and thereby also get further along in the development of policy. It will decrease the cost, which is a central element, and it will decrease the technical challenges, because if we have an alternative ballistic re-entry, we can perform the docking that we already know pretty well from the International Space Station, and thereby avoid the development of parachutes and heat shields needed. Last but not least, this will decrease the limitations on the sample size, as we will not go with the ballistic re-entry. Just briefly, this is the way that the timeline, so to say, looked before SEDNA. So there will be a launch from Earth. It will go to the icy moon, where it will sample, and then return back to Earth. When we introduce SEDNA, we get this blue dot here in between, which is the bottleneck that I was talking about. The architecture of our platform looks like this. It's built up by 3 inflatable modules, and it will, from Bigelow Aerospace. One of them will be a sterilized module with only robotic handling of the samples. The 2 other modules, the crew habitat and the storage module, will be able to support life and will also be able to be used as transport back to Earth if anything would be to happen and we need to evacuate. The whole element will be inhabited by 3 scientific astronauts who will be able to perform the scientific experiments through the robotic, via the robots in the sterilized module here. Everything will be brought up, the modules will be brought up on a SpaceX heavy Falcon launcher, and Dragon modules will be Dragon capsules will be used to send up the astronauts. And I will now pass the stage for final recommendations and conclusions to Stan.
Thank you, Alexandra. So this presentation is the culmination of all the work of the SEDNA team. In the presentation, we've introduced rationales for missions to the icy moons and planetary protection. We've looked at existing planetary protection policies and procedures and management. We've looked at quite a number of mission concepts, planned and conceptual, and we've also analyzed the NASA technology roadmap. And all this has led us to make recommendations along the way, and these recommendations lead us to propose these final two concepts, which we hope are springboards for more discussions of projects. So the two main proposals are prioritizing the technology roadmap in terms of planetary protection score for each technology, as well as developing an orbital platform for sample return missions. And we believe this is important because it can help bridge the institutional barriers that in planning between robotic and human missions inside agencies. And it may also help us bring together a more international outlook and consortium together for getting more international agreement on planetary protection policies. So we have a number of further recommendations for further research, which mainly involved in analyzing the technology roadmap. We need better tools for assessing the potential costs and potential difficulties in technology investment in upgrading from, say, TRL level 6 to 9 or from 3 to 7. We looked at this and couldn't really find a great metric for proper costing estimations of this. As well, we would recommend standardizing the planetary protection score and coming up with a quantification of it. Our first attempt is just a first attempt, and further refinement of our conceptual design for the SEDNA platform. So with that, I'd like to invite the whole team up to respond to questions, and thank you very much.
Okay, thank you all very much for a very good presentation. What I'm going to do now is to hand the microphone straight to President Peters, because I've just had an email to say that there's no sound on the live stream at the moment. So I'm going to run to the back and have a quick chat with the techs over that. And we have at least one question for you from NASA, which I will come back to when I know that they will be able to hear the answer.
Okay.
Also from my side, thank you for that very comprehensive discussion. I go back a little bit to the beginning. You made a generic statement about the ethics, but let me now go really down to earth. Well, or down to an icy moon, as you want. Imagine you have a lander. The lander finds in a few minutes or in a few hours that there is some primitive life, like bacteria. Now my question to you is, real question is, what do you do then? Interrupt a mission and say, we let this life develop, like McKay is saying, or you do like Robert Subber and say, I just step on it, it's MIUFA. What are you doing? You find bacteria after a few hours.
Well, I think this question would divide our team quite a lot, actually. So we might have a duel in front on the stage here for you. But for myself, I would say that for myself, finding the life would be enough, and we should have some time to study it. But there should be some time. It depends on which environment, I suppose. If it's Mars, I would say let's go colonize it anyway. And if it's Europa, we're not going to go there anytime soon, I think. So, but does anybody else want to? Yeah.
Yeah, so I would just like to add that this is one of the reasons that the international cooperation on space, on planetary protection policy is so essential, because this is not back in the 60s when America went to the moon. It was America who did it and planted an American flag. If we do this, we're going out there as the whole Earth. That's one of the reasons that the work is there for getting a cooperation on planetary policy, and it should be something that there were some rules about before. So I don't think the decision would be made in that case of discovering the life. Hopefully we would have already at that point a road plan just to come out of the cooperation.
So yeah, and to tie it back to our presentation, the scientific rationale would be it's enough to discover, and then if you want to discuss the other social and ethical rationales, that's where there's a lot of room for more disagreement on the issue. Anyone else?
Okay. Well, congratulations on a very professional presentation. It was very enjoyable and very informative. I'm going to ask a question about the SEDNA platform. So from my perspective, it seems like a very costly recommendation to put an orbital platform up there to support COSPAR 5 missions. Mm-hmm. Looking at the CONOPS for what you're doing, your sample return capsule will come back to an Earth environment, slow down, and enter a low Earth orbiting state. It will then be rendezvoused and docked with your orbital platform. Mm-hmm. Astronauts will take it inside and start playing with it, and then repackage it and send it down on a Dragon re-entry capsule. Is that broadly correct?
Broadly.
Okay.
I'll give you broadly.
Yeah. So my question, or my question is what is the justification for this orbital platform as opposed to just docking it with a Dragon to bring it down, if that's all you want to do?
Well, the key thing here is that we would have the return capsule dock on this side and the astronauts dock on this side. So there would be no
and attach itself somehow to the Dragon capsule and just come down that way without the need for a big orbital platform.
The Dragon capsule won't be used to bring the sample back to Earth. The whole idea of it is that the laboratory that we would have on Earth to investigate the samples is now placed in LEO. And all the experiments that we would perform on Earth to know what was going on would be on the platform. In that way, it also means that if what we get back, we realize that this has it poses a threat, then, well, roughly speaking, we only risk 3 lives rather than an invasion of some sort of parasite or whatever that we wouldn't know what was on Earth.
And just one last point. I mean, for us, this is a good discussion because our main goal was to be provocative in presenting this proposal so that we could talk about what combination human and robotic missions we could have without forcing every robotic sample return mission into a ballistic entry return and straight to Earth.
Okay, thank you.
We actually report, we do have a budget outline, at least of the initial construction phase. I think it would be research into the continual maintenance and then eventual deorbiting of the platform, but it is something we've considered, and there is more information in the report as far as...
Which one is that?
Yeah, okay. I'm just putting up the budget slide.
Okay.
The other way.
No,
Yeah.
at the end.
Yes.
Go ahead. Go.
Okay. Yes, so I think that answers the question. Thank you.
So we did have a cost estimate for it, and we know it is expensive. But also, we also know that because of the timelines in the robotic missions, it wouldn't be something that would have to be launched until well after the lifetime of the ISS. So this really presupposes that NASA would have some LEO infrastructure that would replace the ISS after that, perhaps a network of Bigelow structures or other smaller orbital stations as well.
Can I answer that? Yeah. So just to add as well, so one of the arguments for this platform is that although there is an investment in the construction and operation of the platform, then there will be cost savings in the development of interplanetary probes, and in particular the sample returns. So they will not need heavy heat shields. They will not need to protect the samples from ballistic re-entry and so on. And we believe that through that, and through successive interplanetary missions, we can make cost savings.
Okay, yeah, thank you very much for that great presentation. Really enjoyed it, reading and listening to you. Just looking at the extra slide, maybe just some comment. Decontamination, you put a figure, a number there. But if we find alien life forms that evolved in a Titan Enceladus environment, they may demonstrate a biochemistry that is completely unknown to us. So decontamination works for terrestrial life forms. So we may have to look into further research. How do we decontaminate from a life form that we don't know yet? So putting a figure maybe, well, it's like gambling. But the question I have is a little bit more towards the PP score. I understand it's still a little bit in the infancy, and which you developed, but maybe you could talk me a little bit through your PP score, which I think is an interesting approach in trying to foster certain technology advancements and progress, but I did not completely understand how you come to your numbers and figures. That was 52 and upwards, I think, on your slides.
Yeah, it was, so the graphs in the slides were more showing the, so in the full report we had two scores. One was an achievability score, which was just based on the TRL level you start from and what you have to go to and the amount of time you have to do it in. So that was our replacement for cost, because we couldn't come up with a good metric to take all that and come up with a development cost. So we had that score, and then the other score we had was the PP score, which is just from -5 to +5. And it was based on most of the, I would say about half the technologies, do you remember, Will, were neutral, because they didn't really have an impact on planetary protection one way or another. You got a positive score if it was deemed that you made the technology made the planetary protection requirements easier to achieve. So if for some reason you increase the reliability of your spacecraft, so you reduce that chance of contamination, because the principal planetary protection requirement is 10 to the -4 chance of contaminating a foreign body. So if you can increase the reliability of your flight dynamics or your EDL, and you know what you're targeting, you know where you're going to land, those kinds of things, then you can reduce the chance of accidentally crashing into some place where you don't mean to be. And then on the other side, the negative side, was any technology that would maybe make it more difficult to clean or to decontaminate the probe, to do if anything that would require the dry heat microbial reduction, because that we had some study that said that adds $100 to $200 million to any program budget, just for that decontamination process. So any of those technologies that would make that process more difficult, we gave a negative score, or make it more challenging, I guess. Is that fair? Do you have anything to add, Will? Okay. All right.
Okay, thank you very much for your excellent presentation. I enjoyed very much, sorry. I have a question, one sample one. What was the criteria which you respect to choose Enceladus as a favorite target?
Sure, go ahead. Yeah.
So I think as far as subsurface oceans, for the longest time, I think Europa was the big candidate, but I think it was recent observations of geyser activity, specifically in the southern hemisphere of Enceladus, that I think have spread a lot of interest. And so just things from even tasting these this water vapor, this frozen material actually coming out that was and of course, I think it was mentioned earlier, the gravity well of Enceladus. So if we're talking sample return, because the gravity well is much lower than the other icy moons, then a sample return is much easier because the whole mass budget with returning it, liftoff, that kind of thing. So I think it just makes Enceladus kind of the more ideal candidate, it would seem.
Okay, thank you.
Thank you.
Next question.
Okay, thank you. Well, thank you very much for the presentation. I enjoyed it a lot also, as well as the report itself. Now, as a former scientific astronaut, I'm very interested, of course, by the SEDNA concept, so I liked it. This I can tell you. But I have questions, of course. Okay. In particular, I understand that the SEDNA will allow you actually to make a preliminary, at least preliminary, testing measurements before making sure that you will not disturb any kind of life later on the planet, on our planet. But from an ethical point of view, so do you plan to do something like the Chernobyl kind, where you send actually people, make them in danger there potentially, and then well, let's see what happens. And then Alexander's remark was interesting. You said it's better actually to just to kill 3 people than more than that. So as an astronaut myself, I cannot accept that, of course. So I will make a suggestion, okay? And then, of course, you will be able to answer to that. Okay, first of all, I think that the this SEDNA platform will not serve only for this kind of science, but could serve also for any other science from the low Earth orbit, okay, including microgravity, including Earth observation, and so on. And to come back to Barnaby's question, I think that this will actually mitigate the question of the cost, okay? But now, coming back to the preliminary analysis of your samples, what I will probably suggest is to have a dedicated module, as you have proposed, but detached from the SEDNA platform, okay, for the first test. So you're on the same orbit, you have some distance, okay, so you have a docking of the sample coming back from your exploration, and because it will be done robotically anyway, okay? So you don't need to have the astronauts close to it, even though it is just 5 meters or something like this. So you could make preliminary tests robotically on the same orbit, but far away, and everything goes well, so you can reattach to the module and continue working on it. And it will probably save your scientific astronauts, and I like that. So answer on this particular topic? Chernobyl workers and and other ways to make it?
I think that the first point is that really depends on the project managers and how they feel. Currently, we don't feel so bad, so I don't think we would do that. But again, and I think this connects to Walter Peter's comment as well, that the choice of a mission and the actions taken in that mission really depend on the agency that supports this mission. And what we encourage is international collaboration and cooperation, so we have some kind of uniform process. So either we agree to do Chernobyl or we don't. But I think this team would probably be against the idea of sacrificing anybody for this. Yeah, please.
I just also want to add that every time we send people to space, we send them to an environment where the chances or the risks of something harmful happening to them are larger than they are on Earth. Having astronauts on the ISS in regards to space radiation and all these things. And I know that NASA, for instance, has certain rules about the probability and the risk of developing cancer because of being in space and all these things, it has to fall within certain limits. So I would anticipate that in this case that the astronauts would know that there were certain risks involved in the same way as I mean, it's always been the case for the explorers that we send out, and that the responsibilities of the agencies and the people behind them then is to, before making this drastic step and putting them at this risk, having done everything that is possible for us to mitigate them at a point where the risk of it actually being dangerously harmful to the astronauts is so low that the probability of it happening is not something of a major concern. But there's still a big difference in putting people who've chosen to go to that platform at risk rather than all of the people on Earth who have not necessarily had a vote in what's going on.
Well, it's not exactly what I expected. I think that if you send astronauts in space, they are taking risks, that's it. But there is actually a frame in which actually these people are working today and are taking risks. So I would like that you, in your particular case here, so you keep inside this frame, okay? And this is why I'm suggesting actually to have a preliminary robotic analysis of your sample far away from the space station on the same orbit, and if everything goes well, so you can dock and then continue working on it.
I think we all agree.
Thank you.
Yes, yeah, absolutely.
I just want to point out that I think that Alex want to point that there are a couple of people here who want to go to space in any frame, so they are ready to.
Many thanks, Team SEDNA, for a very interesting presentation with solid academic content. Just one comment and one question, if I may. Martina, you mentioned something to the effect that NASA was interested in astrophysical bodies with water chemistry and energy, something to that effect. It's actually organic chemistry. It's not chemistry as such, organic chemistry. Things like alkanes, stuff like that. My question is this. I kind of expected to see more references to the European Science Foundation's planetary protection activities, because your work to some extent was inspired by them.
That is true, but I believe their study is just starting to get underway at this point, so we didn't really have any information from what they were about to do. Actually, we know what we imagined doing was putting together a first analysis of the technology roadmap that might be useful in their study, and we would certainly love to forward this. I believe Dr. Tetsis already has a copy that might be useful for their PPOS study, which is, I believe, started 2 months ago.
But to what extent did you interact with Emmanuel Detsis, for example?
Well, we had first contact with him in brainstorming and picking the subject area back in December, January timeframe, and he gave us direction about the study. But I think, to be honest, they weren't going to get started before we had to be done our first draft. So we didn't really have a lot of crossover with what their team was doing.
But do you anticipate some follow-up with the European Science Foundation?
Yeah, I believe that would be a great avenue for further research, actually, yeah.
Brilliant, thank you.
Right, thanks very much. Very interesting presentation. I was pleasantly surprised not to see little green creatures coming out of the slides. And I also like your strategy of presenting the cost estimation in the auxiliary slides. I think this is you've learned some lessons very well. Key question: you seem to have a very specific architecture in mind, at least in terms of the consortium or the elements that you would utilize, very specific industrial, let's say, partners, etc. Have you looked at a trade-off analysis? Because if you're looking at an international collaborative project, I mean, surely there might be other candidates and other partners that would be considered along the lines of the other ISS or otherwise on this. I mean, have you looked at other alternatives besides this specific configuration?
Well, the reason we picked this configuration, it was to actually aid in the costing of it, so that we picked commercially available items to give us the rough parameters for what the costing would be. And of course, what would SEDNA would need to launch, if a robotic mission left now and returned a sample, it wouldn't return for 15 years or so. So we wouldn't be buying these right now and launching them, but we just wanted to use something that would give us today's
That's
dollars
an illustrative,
cost.
okay, that's an illustrative approach.
Yeah.
Okay, that's
Yeah.
And very quickly, on a second point, have you considered, you did a very detailed analysis. I would have preferred to see a little bit more on the SEDNA during the presentation, but you did a very detailed analysis of the future missions and planned missions and undergoing missions, etc. Have you considered the implications to these missions from the, let's say, materialization of SEDNA? I mean, would they, I mean, how would they change in terms of orbit, in terms of docking, in terms of selections? I mean, have you gone into this level of detail? I mean, this also perhaps follows somewhat the NASA approach, the NASA question that we heard. I mean, have you looked into that level of detail?
Sure.
And that's it from me. Thank you.
So in the sense of looking at the exact orbital trajectories, no. But we infer with our proposal that we would have changes to the systems and subsystems of our interplanetary probes. The probes would have to be designed to dock with the SEDNA platform. However, they would no longer require a heat shield or a parachute or the guidance systems to re-enter the Earth. They would, of course, require the guidance systems to enter a low Earth orbit from an interplanetary orbit, and also to dock with the platform, of course. Yeah, please. Yeah.
I would also like to add that the concept that our primary concept of SEDNA is, as has been stated several times by now, that it is a concept and it is a thought experiment, and we wouldn't anticipate that when this actually, if it got off the ground, that, I mean, that would still be way down along the road, and the missions that are in the pipeline at the moment would at that point have been actually sent off and gone to the moons that they were. For the ones that are more thought experiments and not actually on the drawing board yet, when it comes to astrobiological missions, it has been seen several times that it's one of the first areas where there is cut when, for instance, NASA goes through budget cuts. And a lot of the missions, for instance, the Clipper mission, the flyby missions that were discussed earlier, have been changed several times. So therefore, it would not necessarily be a bad thing for either of those if some of them could be combined in the future. But for the presently planned ones, it wouldn't affect them.
Okay, we have a follow-up comment from NASA, which will be the kind of last comment question of this session. From Catherine Connolly, responding to your earlier response. She says the discussion doesn't really capture her point, which is that to make life detection measurements, the instruments have to be extremely reliable and the samples have to be extremely clean, better than we yet know how to do on Earth. And so if we want to do this in orbit with sufficiently high confidence, it would be extremely expensive. And then a second thing, which actually comes back to the discussion about scientist astronauts, maybe Professor Favier could respond later. He says, if there were containment breaches, can we be confident the astronauts would admit to it? Because the lunar receiving lab technicians did not and ran away to avoid being quarantined. So one last response, and then we'll wrap it up.
May we defer the question to Professor Favrier?
Well, the main one was about the cost and difficulty of making these instruments in space when we can't properly do them on the ground yet.
Right. Well, again, this is a proposal for an improvement on the existing methods. And the existing methods are to fly something that is perhaps not very clean to somewhere which may have life, potentially contaminate that environment, and then bring back something which may potentially contaminate our environment in a relatively controlled way, but of course with risks. So our proposal is to add some further protection to mitigate the risks, so that in low Earth orbit it would be easier to place more scientific equipment and to conduct more accurate and productive scientific analysis in low Earth orbit than on Enceladus, for example. It would be more expensive to send the equipment there, and so on.
Okay, well, thank you very much, and thank you very much to everybody in Team SEDNA for all your hard work both today and over the last 6 months. Congratulations. For those people out there watching online, apparently 50 people are watching online, we will now take a 15-minute break and then reconvene for TP Lunar Hatha.